Hello and welcome to this fourth lecture of Introduction to Artificial Intelligence and Machine Learning for Engineers. So today we are still going to talk about AI, so artificial intelligence approaches to solve problems. So as a reminder, we are talking about here about problems for which you start from a given situation. Then you have a series of different choices that you can make. And based on those choices, you will move to a given state. And once you reach a new state, you have other choices that you can make. And then your goal is to find the best sequence of choices that ultimately bring you to your goal. So this is a very general class of problems. It can be to find the shortest path to go from a given position A to a final position B, or it can be like more general, like playing a game. What's the best combination of moves that you can take, that you can do to win the game, or any kind of problems where you have to make some decisions, and every time you make a decision, you have some new choices that becomes open to you. All those problems, they can be like represented as a tree where you start from an initial state. You have a series of choices that brings you to a different state ABC. Then from each situation ABC, you can make some new choices, and at some point there is one branch that will bring you to the goal, and you want to find what's the sequence of choices that you have to make to achieve your goal. So far we have seen different types of search algorithm that allows you to explore this tree and to find a combination of sequences that allows you to reach this goal. But so far the algorithm that we have seen, they are not very smart. Just to show you an example, like just imagine that you are starting at an initial position I, and your goal is to go towards a position G, and for this you have different routes that you can take. So different routes that brings you to different states. If you just have something like this, then the algorithm that we've seen, the depth first or the breadth first, there is no guarantee that they will bring you towards the closest direction. For example, in those algorithms, it's very likely, or it's very possible, that you could start in this direction and that you eventually continue in this direction, and then maybe you will try this direction and this direction before you eventually find that there is a path like this that allows you to reach the goal. So in this case, the algorithm that we have seen, they are referred to as uninformed, because the only thing that they are doing is to start by the initial position and then gradually explore the tree, gradually explore the branches, that the different choices that you can make. So it gradually move from the initial state towards the different nodes of the tree, but it doesn't know if it's getting closer or further away from the solution. It doesn't know that if it's going in this direction here towards the left, it doesn't know that it's actually getting further away from the goal, and it doesn't know that it would be a smarter idea in this case to go towards the right to get closer and closer to the goal. So what we are going to talk about today is a second class of search algorithm, which in this case is informed. So those algorithms, they use some knowledge about how far you are from the goal, or how far have you traveled from the initial state, and they will use this knowledge to either accelerate the search of the optimal path to go from the initial position to the final position, or either to make sure that the path that you have found is the path that you have found between the initial and the goal state is indeed the shortest path. That is to say that if you find one way to solve this problem, if you find one way, one sequence of action that allows you to go from the initial state to the goal state, it can those kind of algorithm can make sure that you have found the optimal solution, that you have found the way to achieve your goal while doing the minimum number of different actions, for example. So to apply these types of algorithm, you need to have some information about the cost that it took you to do those actions, or you need to have some information about how far are you from the final goal. So in general, one thing that you can always know is how many action have you taken so far. So if you start from an initial situation and you have reached a given state, you can always say, okay, how many action did I take so far? How many action have I taken so far? So for example, if you started from a given problem where you had the example that we saw last time, where you had a given farmer and the dog and the sheep and the lettuce on one side of the river, and your goal is to bring all those three things towards the right of the river, on the other side of the river, then the number of action that you took is how many times did you cross the river. So did you cross the river 1 time, 2 times, 3 times? And in this case, after each sequence of action, how many times you cross the river, and that's the total cost of your search so far. And your goal in this case, for example, could be to cross the river while minimizing your goal would be to bring all those 3 items towards the other side of the river while minimizing the cost, which in this case would be to minimize the number of times that you cross the river. So this is about the cost. This is about how far have you traveled so far? How many actions did you take? How much did it cost you to take those actions? And then the other information is, once you take those actions, how much closer does it bring you to the final goal? And sometimes you don't always know that. You don't know if the action that you're making, if they are actually getting you closer to the goal or not. But very often you can either calculate, or sometimes you can estimate how close are you from the final solution. For example, in the case of the river, you can measure how close you are from the final solution by counting how many items you have brought to the other side of the river. You start initially with the dog, the sheep, and the lettuce that are on the near side of the river, which means that in this case you have moved 0 items to the right side of the river, and eventually your goal is to bring those 3 items to the other side of the river. So in this case, you will have 3 items that are on the far side of the river. So based on this, it means that any intermediate state, when you have brought for example, if you only bring the dog to the right side of the river, to the far side of the river, then your measure of success could be 1. Why? Because you have brought 1 item out of 3. So the distance from the final solution in this case would be 2, because you are still missing 2 items. If you bring to the far side of the river, if you bring the dog and the lettuce, then your measure of success would be 2 out of 3. So it means that now you are getting closer to the solution. So because you are missing only 1 item. So in this case, the number of items that you are missing from the goal of your problem could be used as an estimation of how far are you from the final goal. So in many cases, you can quantify like this, or roughly estimate how far you are from reaching your goal. Another example is if you play a game, like a chess game, for example, you can measure how far you are from your goal based, for example, on how many more pieces do you have as compared to your opponent. If you have much more pieces and your opponent has lost a lot of pieces, then it means that you are probably very close to victory. But if your opponent has much more pieces than you, then it probably means that you are very far from victory, which means that in this case you will try to do moves that bring you closer to victory rather than take some moves that bring you further away from victory. Another example could be if you just want like to design a GPS that will allow you to travel within a map and to take to choose the road that can bring you the fastest to your destination. Then in this case it's very easy to measure like how close to your goal you are, because you can just use the distance, the actual distance in kilometer or in miles from the destination, gives you a measure of how close you are from your goal. And if you use this information, then it becomes very obvious that if you start from this initial position like this, then the right choice initially will be to move in this direction, because this is the one that brings you closer to your goal. So it's in this case it is not useful to explore the other direction, because it doesn't bring you, it brings you either further away to your goal than your initial position, or potentially it brings you closer to your goal, but there is another branch that brings you even closer to your goal. So you will initially favor the branches that always bring you closer to your final destination. So as a reminder, the general algorithm to do a search is as follows. So you start by the initialization, that is to say, you define your frontier f as initially being only the initial state, the state that you start from. Then the next step will be to check if the frontier is just empty. So if the frontier is empty, if there is nothing in your frontier, then it means that you have failed your search. This is a failure. As a reminder, the frontier is the list of all the states that you have discovered so far. So initially you know only one state, which is the initial state, and then little by little you are going to expand the nodes of your tree. You will find more states, and then you need to pick what is the next state that you want to explore. So initially you know only the initial state. So the next thing you're going to do is to check if your frontier is empty. If your frontier is empty, it means that you have exhausted all the possible states that you knew, and you didn't find any. You didn't find the goal, which means that your search has failed. But if you still have some state to explore in your frontier, then the next step will be to pick a state n from the frontier. So you will look at your frontier, you will look at this list of state, and you will pick one state n from this frontier. So this is where each algorithm, each search algorithm will differ. You have different rules on which state to choose from the frontiers. Then after you have chosen this new state, then you will check, is it the goal or not? Were you lucky? Did you find the goal or not? So this is a condition. If you found the goal, then your search is a success. You have found a way to find a path, a sequence of action that brings you from the initial state to the final state. If you were unlucky, then you did not find the goal just yet, so you found a new state. So then you are going to, or you selected this state that you found previously, so you are going to now expand this state. So you are going to add all the successors, so all the nodes, all the states that are connected to this state n. You are going to add them to your frontier. Now you discovered some new states, so you are going to add the successors of n. You are going to expand the node n and add it to the frontier f. So that's the next step, the next operation. And then since now you have fully visited the state n, you're going to remove it from the frontier. So you are going to remove it from your list of state that needs to be visited. Now you have visited n, you have realized that it is not the goal, you have expanded n, you have found all the other states that are connected to n, so now you have added those new nodes to the frontier to be visited for later. And now so you can remove and you have fully evaluated the state n, and you realize that it's not the goal, so now you can remove it and go back and start doing a new iteration. Check again if the frontier is empty, pick a new state, check if it's the goal, etc. So now the question is, in this case, the different algorithm, they will differ based on how do you choose the state n from the frontier. And so far the different rules that we saw is the depth first or the breadth first search, where you only choose the states that you have found, either the oldest state that you have found, this is the one that you will pick, or the newest state that you have found, which is another way to explore your tree. So in this case now, so those two algorithms, they were uninformed, like you just choose the state based on how late or how early did you find this state. But this is not a very smart way to choose a state. Now we're going to see some algorithm that gives you a smarter way, an informed way to choose a state based on how close you are from the destination. So for this, we are going to now talk about what we call the greedy algorithm. So now we are going to introduce the greedy algorithm, which is again a search algorithm, but this time it's an algorithm that is informed. It means that it benefits from some knowledge that you have about your problem, and based on this knowledge you will be able to make smarter choices to go more towards the direction, the final destination, rather than wasting time exploring some branches that actually bring you further away from the final direction. So in this case, in the case of the greedy algorithm, the idea of this algorithm is when you pick the state n from the frontier, you will always pick from the frontier the state that is the closest to the goal. So in this case, you will pick the state n that is the closest to the goal. That is the closest to the goal. So what does it mean to be the closest? So again, for this you need to know how far away are you from the goal. If, for example, you are trying to find an actual path on a map, then the distance in this case, you don't know how far, how much more you need to travel from this state n. For example, it's if you're trying to find the optimal route, the optimal sequence of streets to take in order to go from an initial position to a final position, then you will pick a given state, which will be some kind of intersection somewhere on your map, a point where you have different routes, a different path that you can take. And the only information that you know is how far are you from the goal. But you don't know necessarily how much more distance do you actually have to travel. Like the only thing that you know is if you were a bird or a plane, if you were able to travel in straight line from this state to the final destination, how far are you? So just to give you an example, like if you start from the initial state like this, and then if you have two choices, A and B, and then you know that your goal is here. For example, state B is at 3 miles from the goal, state A is at 3 miles from the goal, then you will tend to favor state B because it brings you closer to the goal. But in this case, 3 miles corresponds to the flight distance, like it corresponds to the, if you were able to fly directly from state B to state G, it would take just 3 miles. And if you were able to fly from state A to state G, it would take 4 miles. It doesn't tell you that the actual road is going to be 3 miles. Maybe the actual road is much longer than 3 miles. It cannot be shorter than 3 miles because 3 miles is the distance in straight line from state B to state G. But maybe it's possible that actually the actual route from state A to state G could actually be shorter than the route between state B and state G, but at least like the flying distance is smaller in case of state B. And the reason that you are using the flying distance here is that in many cases, if you have a given state, you can estimate how far are you from the final destination, but you don't know if this is going to be really the real distance that you will have to travel from this state. For example, if you want to see if you want to go to a given mountain, maybe you can see this mountain from very far away, so you can estimate how far you are from this mountain just by looking at it. But just because you can see the mountain and because you can see that you are not very far away from this mountain, doesn't mean that you will be able to easily reach it, because you don't know what are the streets that will allow you to take this mountain. And maybe there is no direct street, there is no direct path that will take you in straight line from where you are to the mountain. Maybe you will need to do a giant detour to reach this mountain, but this, you don't know it from the beginning. To know this, you need to go explore your tree, and you need to expand the nodes to discover what are the branches that will eventually allow you to reach this mountain. But if you knew already all the details of the map, then it would be very easy to directly find the shortest path. Here, you are discovering your tree little by little as you expand the nodes. So the only thing that you know is how far are you in terms of flying distance from the mountain, but you don't know what is the real distance that remains to be done. But nevertheless, just knowing this information about how far are you from the mountain in terms of flying distance will allow you to make some smart decision, because you will favor starting to move towards the mountain rather than starting to move in the direction that is the opposite to the mountain. So let's see an example of application of the greedy algorithm. So for this, let's consider that you have an initial state I. So this is your initial configuration. And eventually your goal is to reach the state G, which is the goal of the problem. So your goal is to reach this position, to reach this state. Then you have some intermediate state that you will need to take. You don't have an immediate action that allows you to go directly from the initial state to the goal state. So you have one state A like this. You have one state B like this. Then you have one state C like this. You have one state D like this, for example, and then those states are connected to each other by some transition, by some actions that you can take to go from one state to the next. Or if you are considering this to be a map, then those will be some routes, some paths that are connecting those positions. So let's assume that there is a road here, you have a road here, a road here, a road here, and then you have a road here and a road here. So this would be some kind of a map with different roads that are connected to each other at some intersections. So then in the case of the greedy algorithm, what you need to know is what is the distance from the final goal. So if you have reached the goal, then the distance from the final goal would be 0. You have reached the goal. So let's assume that at state C, the distance would be 2. The unit doesn't matter. It could be 2 miles, 2 meters, 2 kilometers. Let's assume that the distance of the state D from the goal would be 3. Let's assume that the distance of B from the goal would be 3 as well. That the distance of A from the goal would be 4, and that the distance of the initial state from the goal would be 5. So here this map is clearly not at scale, but let's just explore it as an example. So in this case, in the case of the greedy algorithm, so you would start initially by expanding the node I. Initially, your frontier only comprised of the state I. Here you have 2 choices in your frontier once you expand your initial node I. You have state A and state B that will belong to your frontier. Here in this case, you will pick the state B. Why? Because it brings you closer to your final goal. State B is at a distance of 3 from the goal, whereas state A is at a distance of 4 from the goal. So you will pick state B and you will expand state B. So when you expand state B, you have 2 successors to state B, which is the state C and the state G. And in this case, you will now pick the state G. Why? Because this is the one that is the closest to the goal, because in this case this is the goal, so the distance is just 0. So in this case you have very efficiently found the shortest path that allows you to go from the initial state to the final state. And it's very efficient in this case because you never had to expand the state A to expand the state C. You never have to worry about what are the successors of A and C. If you were to do, for example, a breadth first search, then you would have first expanded the state B, then expanded the state A, then expanded the state C, etc. So it would have taken much more time to find the path that allows you to go from the initial position to the final position. And in this case, like, the reason that these types of search is pretty smart is because if you had some other possible state that are some successors of the state I, like for example if you had a state E here or a state F, then you know that you would have never explore those states, because they always bring you, like this one could be for example at a distance 6, this one could be at a distance 7, so you know that if you pick those states they would actually bring you further away from your goal. So in this case it is very unlikely that you would choose those states, because you can always find some other states that brings you towards a more promising direction, brings you to a state that is closer to your final goal. So the main advantage of this greedy algorithm is that it can be very efficient. It can be much more efficient than the other search algorithm that we saw, and it can give you a possible solution that is by minimizing the computing time. But sometimes it doesn't necessarily give you the most optimal solution. So let's take another example just to see a case where the greedy algorithm would work. It would give you a solution, but just not the best optimal solution. That is to say, the solution with the minimum distance being traveled to go from the initial position to the final position. So let's take another example where you start by your initial state like this, and then you have your goal state on the right, and then so let's assume that you have a given state here, you have another state here, you have, let's assume that you have another state like this, a state like this, a state like this, and then those states are connected to each other this way. So now, starting from this tree, if you apply the greedy algorithm, let's assume that the distance here of each node So it would be 0 for node G. Node G is directly the final destination, so the distance from the goal would be 0. Then let's assume that the distance of those two nodes from the goal would be 2. Then the distance of this node from the goal would be 3. The distance would be 4 here. The distance would be 5. And then the distance of the initial state from the goal would be 7. Again, this map is clearly not at scale, but let's just take it as an example. So in this case, so you start from the initial goal. Then you have two choices. You have two potential successors from your initial node. In this case, you will favor this one because it brings you closer to the final goal. Then starting from this, you have two choices. So either you can move to this one, or you can go back and explore the initial state here. In this case, you will favor now this one because it is only at a distance 3 from the final goal. Then you will expand this node, so now you will find this new state which is even closer. So again you will go in this direction, and then starting from this point, then you will find the goal, and the algorithm will stop because it has found the path from the initial position to the goal. In this case, so the path that you will have found would be to go this way, so to do this path. But in this case, so you have found the solution to the problem, but it's not the optimal solution, not the optimal solution. Why? Because this solution definitely works, but there is actually, in this case, a better solution, which would be to go in this way and to directly reach the goal in a much shorter way than to do this zigzag by going on the top of this map. So in this case, this is an example to show that the greedy algorithm can be very efficient, but it's not necessarily, it doesn't satisfy the optimality condition. It doesn't necessarily give you an optimal solution at the end. It gives you a solution, but you cannot be sure that it is the optimal solution. You cannot be sure that there is not another path, another sequence of action that potentially could have been more efficient. In this case, the algorithm just choose to go through from this route just because the initial step brings you closer to the solution. So it disregarded this state here because it was initially further away from the goal, but actually going through this state would have been a better choice on the long term. But it just favored the short-term benefit here by just favoring always only the next best move that just brings you closer to the final solution on the short term, but not necessarily on the long term. So the next question now is, how can we be sure whether we have found the most optimal path or not? How can we make sure that we have found the most optimal solution to a given problem? So for this, we're going to see another algorithm, which is also an informed search algorithm, which is the branch and bound search. So in this case, this algorithm will be also using some knowledge about how far you have moved, but in this case, the knowledge that this branch and bound search algorithm is using is not how close are you from the final goal, how far are you from the final goal, the distance from the final goal, the flight distance from the final goal. In this case, it is not using this information. The only information that it will be using in this case is how far have you traveled since your initial state. So in this case, the idea of this algorithm is that it will pick every time you have to make a choice and pick a given state from the frontier, rather than picking the state that is the closest to the final destination, which sometimes can induce you to make some wrong decision. What it will do is that it will always pick the state for which you have traveled the less from the initial state. So in this case, it always pick from the frontier the specific state that it picks is the one that minimizes the total distance traveled from the initial state. So it picks from the frontier F the state N that minimizes the total traveled distance distance from the initial state. So here there is a one major difference between the greedy and the branch and bound search. The first difference in that in this case, you don't need to know how close you are from the final destination. This algorithm does not use this information. The only information that it uses is how far have you traveled from the initial state. And this is something that is always accessible, because you can always say, okay, the distance that I have traveled from the initial state could be, for example, how many actions have I taken so far, or it can be, if you are moving on a map, it can be how much did I move so far, how much did I travel. So here the information that it will be using is the traveled distance from the initial state. And the other difference between this algorithm and the greedy algorithm is that the greedy algorithm uses the flight distance from the goal state. It uses the distance from the goal state if you are able to travel directly as a straight line from this specific state to the goal state. And the reason it uses this flight distance is because it doesn't know yet what is the rest of the tree. So it doesn't know yet if the road that allows you to go from this state to the goal state, it doesn't know if it's a straight line or if it will be a very long road that makes a big detour. It doesn't know that without having explored the tree. But in this case, what you are using here is not the distance to the final destination, is the distance that you have traveled already. So the distance that you have traveled already, in this case, you know exactly what is the distance that you have traveled already. So in this case, it will not use the flight distance, because it knows the tree, the portion of the tree that you have explored so far. So in this case, this algorithm will use the real distance that you have traveled so far. So if the road was not a straight line, if the road was more a detour, then it knows this information. It knows that you have traveled a lot already. So it will use and benefit this information to identify the path that is the closest, the shortest path between the initial and the goal state. So let's see an example to illustrate this algorithm. So let's consider the following example to illustrate the branch and bound algorithm. Okay, so let's consider the following map. So we are going to take exactly the same map than the one we used before for the greedy algorithm, the one for which we found that the greedy algorithm can give you a solution but not the shortest solution. So in this case, so you're starting from you have the initial node here, you have your final goal on the right, so you have a state D here, a state E here that are connected to each other like this, and then you have a state A like this, a state B like this, a state C like this that are connected to each other. So in this case, in this algorithm, we don't need to know the distance from the final destination. So this algorithm is a good fit when you have a problem for which it's very hard to estimate when you have reached a given state, like how close is it from the final solution. So what you know in this case is just the length of those roads, like the distance between those states, the size of those branches. So for example, you know that if you start from state I, you will need to travel a distance of 2 to reach state A, but only a distance of 1 to reach state D, because state D is closer than state I from the initial state D is closer than state A from the initial state I. Then to go from state A to state B, you will need to travel another distance of 2. Then to move from B to C, you have another distance of 2. Let's say you have a distance of 2 from C to G. You have a distance of 2 between D and E, and a distance of 2 between E and G. So in this case now, let's try to illustrate what will be the different nodes that are picked by the branch and bound algorithm. So again, initially your frontier will be comprised of only the state I. So in your tree, you will start from the state I. Then so you will expand this initial node. So in this case, you have two possibilities, which is state D and state A. And now the information that you will be using in order to pick the next state from the frontier that you want to visit is how far have you traveled from the initial state. If you go to state D, so far you have traveled a distance of 1. So the total distance from the initial state so far is 1 for state D. For state A, you need to travel a distance of 2, so the total distance so far would be 2. So in this case, because in this algorithm you will always pick the state for which the distance from the initial state is the lowest, in this case you will pick the state D. Why? Because the state D is the one that minimizes the distance from the initial state. So now you will expand the state D, so the new state that is a successor of D will be state E. The distance to go from D to E is 2. So now you have a frontier that is made of the state A, which you still haven't expanded yet, and you have the state E. In order to choose the next state that you are going to pick and to expand, you need to look at the state that minimizes the distance from the initial state, state E here. So for state E, you have traveled so far first a distance of 1 to go from I to D, and then you have traveled another distance of 2 to go from D to E. So the total distance for state 3, the total distance that you have traveled is it's 1 plus 2. That is to say, you have traveled a distance of 3 to reach the state E. So now you have two choices. You have the state E, which is at a distance 3 from the initial state, and you still have the state A that is at a distance 2 from the initial state. So now you will pick the state A because it is the one that minimizes the distance from the initial state in the frontier. So now you will expand you will pick the state A, you will expand it and find its successor. So now you have found a new successor B that you add to your frontier. Same thing, you need to now look at what is the distance of B from the initial state. To travel from A to B, you need to travel a distance of 2, which means that the total distance traveled from the initial state for B is 2 to go from I to A, then 2 to go from A to B, which means that the total distance in this case would be 4. So now you have two states in your frontier, the state E, which is associated with a distance of 3 from the initial state, and you have state B, which is associated with a distance of 4 from the initial state. So you will choose in this case the state E because it minimizes the distance from the initial state. So you will expand state E, you find a new state G. The distance to go from E to G is 2, which means that the total distance at this point from I to J is so 1, this is the distance from I to D, plus 2, which is the distance from D to E, plus 2, which is the distance from E to G, which gives you a total distance of 5 so far. At this point, we could think like, okay, we have found G, so let's just stop here. But in this case, your goal is to find the shortest path that allows you to go from I, the initial state, to the goal. So in this case, we cannot stop at this point because at this point, like the state B is only at a distance 4 from the initial state. So if by chance B is very close to the goal, then there is still some hope that you could potentially find a shorter path that goes from I to B and then will go from B to G, because B so far is only at a distance 4 from the initial state, and you have found so far a branch, you have found a path that takes a distance 5 to go from I to G. So there is still hope that there is another shortest path that exists. So in this case, you cannot stop here. You still have to follow the same rules of this algorithm. In this case, you have two states in your frontier, which is state G, for which you have traveled a total distance of 5. Then you have state B, for which you have traveled a total distance of 4. So in this case, even though you have found the goal already, you will pick state B. Why? Because it is the one that minimizes the distance from the initial state. So there is still hope to find a shorter path. So in this case, you will pick B. You will expand B. So you expand it in C. So the distance associated to C will be 2. This is the distance to go from I to A. Then 2, which is the distance to go from A to B. Then 2, which is to go the distance going from B to C. So in this case, the total distance would be 6. At this point, you know that you can stop. Why? Because you have found the state G, and you have found that the other state C is already associated with a distance of 6. So this distance is already larger than the distance that you already found to go from I to the goal. So you know that there is no point in this case in expanding C. It is not useful to expand C because it is already further away. You have traveled already more than the path that you have found between I and G. So in this case, you can just say that at this point you have found, and you can be sure in this case that you have found the shortest path because you have looked at all the other possibilities, and you have seen that for all the other branches, by taking all the other possible paths, you will always necessarily have a larger distance to travel, because at this point at state C you have already traveled a distance of 6. So you cannot possibly find a path going from through this branch that will allow you to reach the final destination, because you have already found here a path that allows you to find the destination with a traveled distance of only 5. So at this point, the algorithm stops. You have found the goal, G, and you have found for sure that there is no other more optimal option than this. So in this case, the advantage of this branch and bound algorithm is that it will give you an optimal solution. So you know for sure at the end of this algorithm that there is no possible shortest path. So that being said, this algorithm can be potentially slower than the greedy algorithm, because in this case, in order to find the shortest path, it took you more computing power, because first you had to expand the initial state, so that was the first one. Then you had to expand the state D, so that was the second one you had to expand. Then you had to expand the state A, which was the third node that you had to expand. Then you had to expand the state E, which was the fourth node that you had to expand. Then you had to expand the state B, which was the fifth node. So in this case, before finding the goal, you had to expand 5 nodes. So you had to explore 5 nodes within your tree before being sure that you have found the goal. So it's slower than for the greedy algorithm, because for the greedy algorithm you just found a path and had to expand only 1, 2, 3, 4. 4 nodes was enough to find the goal in the case of the greedy algorithm. But again, the greedy algorithm was more efficient in this case, but it did not give you the most optimal solution, which in this case is to take this path here at the bottom of the map. So the last algorithm that we are going to talk about is another informed algorithm. And this last algorithm, the main idea is that it combines the strength of those two algorithms that we just talked about. It combines the strength of the greedy algorithm together with the strength of the branch and bound algorithm. And the reason that it can do that is that it uses all the knowledge that we have talked about. It uses the knowledge of how much have you traveled so far, and it uses the knowledge of how far are you from the final solution. And by combining these two types of knowledge as it explores the trees, it can first give you a solution faster than the branch and bound algorithm, but it can also make sure that you have found the most optimal solution. So in this case, the main idea, so this algorithm will be the A star algorithm, the A star search algorithm. And so this algorithm is one of the most efficient algorithms to explore a given tree. And in this case, the idea of this algorithm is, so it still follows the same flow chart as the other algorithm. You will need to create a frontier, and then you will need to pick one state from this frontier. And here, like the rule in order to pick the state is that it will pick the state n. So in the case of the greedy algorithm, we pick the state n that minimizes the distance from the state to the final destination. In the case of the branch and bound algorithm, you pick the state n that minimizes the total distance that has been traveled since the initial state. In this case, you are going to pick the state n that minimizes a given cost function. So in this case, you pick the state n that minimizes a cost function. So a cost function in this case is a given function that gives you the cost associated to picking this state. And in this case, this cost function is equal to the sum of two distances. So this cost function is equal to first to the distance that has been traveled from the initial state, from I, plus the distance to the goal. So in this case, it combines those two information. The distance traveled from the initial state I, this is the knowledge that you used for the branch and bound algorithm. This is the real distance that you have traveled from the state I, and it also uses the other knowledge, which is the one that we used for the greedy algorithm, which is the remaining distance from the goal. So just to make sure we are clear on that, those distances are different from each other. Like the distance traveled from the state I, this is the real distance. This is the actual distance that was actually traveled, so like the distance that you actually drove. So if the route, if the road is not a straight line, if the road is actually made of a zigzag, let's say, like in this case, we take into account the real distance traveled from the state I, not the flight distance. And this is because this is the distance that you have already traveled. So this is based on the fraction of the tree that you have already explored. So you, in this case, you know accurately what is the distance that you have already traveled. So in this case, you can put the real distance. But in this case, the second term of this summation, which is the distance to the goal, you don't know what is going to be the real distance from the goal. You only know how far it is if you were able to fly directly as a straight line. So in this case, this is not the real distance. This is the flight distance. This is the distance if you had a straight line that allows you to go from this state to the final goal. And in this case, you don't know the real distance because you haven't explored the end of the tree yet. You haven't explored the portion of the tree between this state and the final goal just yet. So all you can do is to estimate how far you are from the goal, but you don't know if this is the real distance or not. So in this case, in the case of the A star algorithm, you are going to combine those two things. You are going to combine the distance to the goal, which tells you how far you are. So you will favor some nodes that are close to the final destination, just like we do in the greedy algorithm. But you will also add this up to the distance that you have already traveled from the state I, which is the information that we are using in the branch and bound algorithm. And in this case, you will define the cost associated to each node, the cost associated to each state as the sum of those two things. And you will try to favor the nodes that minimize those two things, the nodes that are close to the initial state, but also the nodes that are close to the final goal. And this is what will allow you to first find pretty efficiently a path that allows you to go from the initial state to the final state, but this will also make sure that you are finding an optimal solution to the problem, that you are finding a path that is the most optimal, a path that minimizes the distance from the initial state to the goal of the problem. So now let's take an example to illustrate how the A-star search is working and how it differs from the greedy search or the branch and bound search. So for this, let's take an example that looks like the previous one, but not exactly the same. So let's assume that you start with a state A like this, and your goal is to reach the state G. And for this, so same thing, you have two possible roads like this. So let's assume that it looks like this, and then you have state A here, state B, and state C, which are connected to each other like this. And so in this case, for the A-star algorithm, what we will need is some knowledge about both the distance that you have traveled since the initial state, but also some knowledge about how far you are from the goal. So we need those two types of knowledge, the knowledge that was used in the greedy algorithm, but also the knowledge that is used in the branch and bound algorithm. So in this case, let's put all the information. So at the goal, you are at a distance 0 from the goal. State E is at a distance 2. State C is at a distance 2. State B is at a distance 3. State A is at a distance 4. State D is at a distance 6. And state I is at a distance 7. And then we also need to know the length of each of those branch, the length of the road. So this road has a length of 2, 2, 2, this one is 2 as well, this one would be 5, this one would be 1, and this one would be 3. And now what we are going to see is by looking at three different examples. So by looking at the greedy algorithm, by looking at the branch and bound algorithm, and by looking at the A star algorithm, we are looking at which algorithm can find the optimal path in this map and which one can find it the most efficiently. So what we are going to do is to solve the same problem with first the greedy algorithm, which is based only on the distance from the final destination. Then the branch and bound algorithm, which is based only on the distance traveled from the initial state. And then we are going to solve it for the A star algorithm, which is based at the same time on the distance being traveled and at the same time on the remaining distance to the final destination. So in this case, so let's start with the greedy algorithm. So you will start with the frontier being the initial state. In the case of the greedy algorithm, so you will expand this node, so you find those two successors. In this case, you will always pick the node that minimizes the distance to the final goal. So in this case, you will pick the goal A because it is at the distance 4, while state D is at a distance 6. So then you will expand state A, you will find the state B. In this case, now your frontier is made of state D and state B. In this case, you will take state B because it is only at a distance of 3 from the final goal. So you will expand it. You will find state C. You will add it to your frontier. Now you will pick state C because it is only at a distance 2. At a distance 2, it is shorter from G than state D. And from this, you will expand this, you will find state G, and state G is at a distance 0, so that's going to be the state that you choose. And based on this, you will pick this path here. You will have found a solution, which is a path that allows you to go from the initial state to the goal state. So here, if we look at the path, the length of the path that it has found. So the path that we found, we needed first 5 to go from I to A, plus 2 to go from A to B, plus 2 to go from B to E, plus 2 to go from C to G. So here that gives us 5 plus 6, so a total length of 11, which we know in this case is not the shortest path. And now let's look at how much computing power did it take to do this. So first you had to expand state I, then you had to expand state A, you had to expand state B, you had to expand state C, and then you found the goal. So you had to expand 4 nodes in order to be able to find this solution. So now let's focus on the second algorithm, which is the branch and bound algorithm, and see what it does. So in this case, you will always pick the node that minimizes the distance traveled from the initial state. So same thing. So you start from the initial state. That's the first node that you expand. You have, in this case, two successors to this node in this case. So you have the state D, for which you have traveled a distance of 1, and you have the state A, for which you have traveled a distance of 5. So in this case, you will choose the state D because the total distance traveled from the initial state is only 1, while it would be 5 for the state A. Then, so you will expand state D, you will find state E. So in this case, you need to determine what is the distance for state E. To go to state E, you need to travel 1 from I to D and then 3 from D to E. So the total distance in this case would be 4. So the distance to go from I to E is smaller than the distance to go from I to A, which clearly shows you that this map is not at scale, but nevertheless, in this case, you will pick the state E, because this is the one that minimizes the distance. Then you will expand state E, you will find state G. In the case of state G, its distance to go to state G is 1 plus 3 plus 2, which gives you a total travel distance of 6. So in this case, now you have state G for which you have a distance of 6, and now you have state A that has a distance of 5 in your frontier. So in this case, in the case of the branch and bound algorithm, you cannot stop here because you cannot be sure that there is not another path going through A that could be shorter than the one going through D and E. The path going from D and E gives you a length of 6, but at the state A, it is still only a length of 5. So at this point, the node in the frontier that has the shortest distance traveled from the initial state now becomes state A. So now you need to expand state A, and at this point you find state B. So you add it to your frontier. Now you need to calculate the total distance traveled from I to B, which is 5 plus 2 equals 7. So now you have a two state in your frontier. You have state G that is associated to a distance of 6, and you have state B associated to a distance of 7. So now you know for sure that this is the goal, and that you know for sure that this path here is the shortest path to go from I to G, because you know that if you take the upper road, once you have reached B, you have reached a distance of 7, which is already larger than the total distance to go from the initial position to the goal, which is only 6. So now you have found a new path that has a length of 1 to go from I to D, plus 3 to go from D to E, plus 2 to go from E to G, which is a total length of 6. So you have found at this point the optimal path that allows you to go from the initial state to the goal state. In terms of computer efficiency, so the number of nodes that you had to expand was first the node I, the initial node, then you expanded the node D, then you expanded the node E, then you expanded the node A. So that gives you, again, you had to expand 4 nodes in this case to find the optimal solution. So now let's focus on the A star algorithm and see how it works. So in this case, so same thing, you start initially by state I. This is your initial frontier. So let's build the tree at the same time. So you start from state I. From state I, so you will need to expand state I. State I has 2 successors. So you have 2 possibilities from this point. You can go towards state D, or you can go towards state A. Those are the 2 new states in your frontier. So to choose the state that you are going to pick and expand, you need to calculate the value of the cost function. The cost function in this case is the sum of 2 things. It's the sum of the distance that you have traveled so far plus the remaining distance from the goal. So the distance that you have traveled so far is 1 to go from I to D, and is 5 to go from I to A. And so in the case of state D, the cost function is equal to first the distance that you have traveled so far, which is 1, plus the distance from D to the final destination, which is 6. So in this case, the cost function for D is 7. When you go to state A, the distance that you have traveled so far is 5. The total remaining distance is 4. So in this case, the cost function is equal to 9 in the case of state A. So in this case, the cost function is minimized in the case of state D. So you are going to pick state D. You are going to pick state D because it minimizes the cost function, which leverage at the same time the knowledge of the distance that you have traveled so far, and also the knowledge of the remaining distance. So the algorithm at this point thinks that state D is the best compromise between how much distance you have traveled so far. You want to travel as little as possible, and also the best compromise between this and the remaining distance. You want, in this case, at the same time to travel as little as possible, and you want to travel in the right direction. You want to travel in the direction that brings you closer to your final destination. So now you will pick the state D, so you will expand the state D. So if you expand the state D, that brings you now to the state E. You need to calculate the value of the cost function. So in the case of the state E, so you have traveled 1 to go from I to D, and you have traveled 3 to go from D to E. So you have your total distance that you have traveled. The actual distance that you have traveled is 4, and the remaining distance, the distance from E to G, in this case is 2. So your cost function now becomes 6. So the cost function associated to E is still lower than the cost function associated to A. So again, you will pick the state E in this case, and you will expand the state E. So when you expand the state E, you find the state G. Again, you need to make sure here that this is the shortest path. So you need to calculate the cost function. So in this case, the total distance traveled to find the state E, the state G, is 1 to go from I to D, 3 to go to from D to E, and 2 to go from E to G. So the total distance that has been traveled in this case is 6. You need to add this to the distance to the goal. In this case, you have found the goal, so the distance to the goal is 0. So in this case, your cost function is 6. So in this case, you have found that the cost function is already lower than the cost function of A. So in this case, you will just pick the state G, and you will just stop there. So in this case, you know that you can stop there because you know that the state A is still for the distance from state A to the goal is 4, and you know that you have already traveled 5. So you know that the shortest possible path that you can find that will go through A will necessarily be at least equal to 9. It's going to be equal to 9 because you have already traveled 5, and you know that there is at least 4 a remaining distance that is at least of 4. So the minimum distance that you can expect is at least of 9. So you know in this case that there is no chance that you can find a shortest path than the one that you have found by using the road that goes through D and E. So in this case, you find the shortest road, which is the one that has a length of 6. And in terms of the efficiency of the algorithm, how many nodes did you have to expand? So in this case, you had to expand the node I, that was the first one. Then you had to expand the node D, that was the second one. Then you had to expand the node E. And after this, that allowed you to find the node G. So in this case, you had to expand only 3 nodes in order to find the goal. So you were able in this case to find the shortest path in a more efficient way than the branch and bound algorithm. So usually the A-star algorithm will always be a preferable choices because it leverages at the same time the strength of the greedy algorithm and the strength of the branch and bound algorithm. So if your goal is to find the most optimal solution, it's always going to be preferable to use the A-star algorithm as compared to the branch and bound algorithm, because it can allow you to reach the final conclusion in a more efficient way. So now so that will conclude our review of the search algorithm to solve problems. Just keep in mind that here we have drawn some maps in order to illustrate those search, but those types of techniques that we have seen, those types of search techniques that we have seen, they are not only specific to maps only. They can be used for any types of problems that require you to make some choices. So every time you have a problem that requires you to make a different sequence of choices, then you can necessarily represent those different choices in terms of a tree. And if it can be represented in terms of a tree with different options, that allows you to reach new state from which you can make new decision, as long as it can be represented in terms of a tree like this, then you will be able to apply those search algorithm in order to find the most efficient way, the sequence of action that allows you to solve this problem. So it's not only specific to finding the shortest path on a given map. It can be applied to any problem where you have to make some choices, a combination of choices in order to reach a final goal for the problem that you are trying to solve.